So if we see here, we're still living in the land of writing explicit formulas and recursive formulas. But now I'm going to change up what type of pattern I'm going to give you. The last video talked about arithmetic sequences, which is a fancy name for linear, adding and subtracting, the same number every time. But if I look here, 3 plus 3 is 6, but 6 plus 6 is 12. 12 plus 12 is 24, so we're not adding the same number every time. It's not linear, or it's not arithmetic. What I see here is that 3 times 2 is 6, and 6 times 2 is 12, and 12 times 2 is 24, and that tells us we have an exponential pattern. But now in Algebra 2, we can also call this a geometric pattern. It's the same thing as exponential. Recursive formulas, just like with arithmetic sequences, start at A1, the initial value. What is the first term in the sequence? Okay? We see here, we can label it first term, second term, third term, fourth term. Clearly, our first term is 3. And our recursive formula is always asking, what did you do to the previous term to get to the next one? So if I go to 12, I'm going to go to the previous term and ask, what did I have to do to get to 12? And we already looked and saw we were multiplying times 2. We started at 3, we're multiplying by 2. Take the previous term times 2, times 2, times 2. Now the explicit formula is going to look like an exponential equation that you guys wrote successfully last week when I just threw it up in the do now. We're going to say a sub n is equal, well, we need the starting value, but this is where it's different than arithmetic sequences. With arithmetic sequences, we had to go back to term 0. We don't do that for exponential and geometric sequences. We have our starting value at term 1, just like the recursive. So we're going to see 3 times whatever our multiplier is, raised to the n minus 1. Test it. We know that the fourth term is 24. So when we plug in 4 here, if we don't get 24, we did it wrong. So if I plug in a 4 here, 3 times 2 to the 4 minus 1, that'll simplify down to 3 times 2 to the third power. 2 to the third power is 2 times 2 times 2, which is 8. And 8 times 3 is 24. Our explicit formula was correct. Now I want you to notice here that we use the same numbers with a geometric sequence. The same starting value, the same multiplier, it's just structured differently. Where with arithmetic sequences, the starting value was not the same. Pause the video, see if you can write the recursive and explicit formula for the problem over here. Okay, recursive. We need that initial condition. It always helps me to number 1, 2, 3, 4. So my A1, my first term, looks like it's 2. And the recursive formula always wants to know, what did you do to the previous term to get to the next one? This one looks a little weird because we see these alternating negatives every other one. So I know that I'm not adding here, I'm not subtracting here, it's just looking a little crazy. So it has to be geometric. There must be a multiplier. I know that 2 times 4 is 8, but 2 times 4 is positive 8. So how do I make it negative? I have to make that a negative 4. 2 times negative 4 is negative 8. Negative 8 times negative 4, negative times a negative, is a positive 32. So that works out with my pattern. So down here, it's times negative 4. If I want number 3, I have to go to the previous term and ask myself, what do I do to negative 8 to get to 32? I multiply times negative 4. My recursive formula is done. Now, just like we talked about over here, if you have the recursive formula, you have everything you need for your explicit formula as well. A sub n will equal the starting value at 1 times your multiplier to the n minus 1. Test it. If we plug in a 3 in there, we should get positive 32. So if I say a sub 3 is equal to 2 times negative 4, 3 minus 1. 3 minus 1 is 2. So 2 times negative 4 squared. Negative 4 times negative 4 is positive 16. Times 2 is positive 32. My explicit formula checks out, and I am good to go.